Hello everyone, welcome to IMSC 685 MIS. Today's we're going to go over another algorithm called K-means clustering. And let's go on to the first part and for the concept lecture. Okay, K-means clustering algorithm. The K-means clustering algorithm is a unsupervised learning algorithm that it will attempt to group similar cluster together in your data, and which means is that there's no features and target actually to train the algorithm. The algorithm by itself in trying to figure out what are the similar group or cluster are. What it does is, in the real-world application, typical application is cluster similar document together as the same group, or in the customer relationship management, you're using this K-means algorithm to cluster customer based on their features and where they are, or the age group, what type of customer they are, the income level, and so on and so forth. And this also leads to for market segmentation purpose, marketing departments fairly using these type of algorithms to determine the product, which type of product sell in which area, or which region, in which segmentation. Okay, and also you can use this algorithm to identify similar physical group, height and weight, and so on and so forth. So this algorithm don't have any training process. It's almost like an optimization algorithm. It takes on the input directly and trying to do the best to figure out what the cluster exists. So let's take a look how this works. The overall goal is to divide the data into the distinct group. For example, the data we have blob we have right here. The observation which each group are similar in distance. So here we can see the data, and on the right hand side after clustering we see there's three groups of the data, cluster of the data actually exists in the data we have. So this is how the K-means algorithm works. So first you choose a trial cluster K. So for example, I just arbitrarily determine a number of cluster K, randomly assign each point to a cluster in the beginning, okay, and then we calculate the center of the algorithm, each one of the cluster, and reposition the center of the each cluster, relocate the center. So basically I calculate the average of your all the data point and calculate the central location for that cluster. Then we come back for each point, we reassign them to the to a cluster who closest to the cluster center. Okay, then we recalculate the center and go on and on again until none of the point got reclustered anymore. Okay, recluster anymore. So to illustrate this concept, we have this slide. This slide shows you in the beginning. This slide shows you in the beginning the data unclustered, so it's all the original data. The step number one, we randomly assign them into a cluster. So there's a no figuring out in the beginning, just randomly assign them to cluster 1, 2, 3, and then calculate the center's location for each one of the cluster based on the population we assign it to that cluster. Okay, then we reassign the data point according to the cluster center to the closest to the cluster center. So we start doing that step 2. Then we readjust the cluster center. Okay, readjust the cluster center location based on the newly assigned cluster group. Okay, then we keep doing that until the cluster center don't move anymore and none of the point got reassigned anymore. So this is a really straightforward algorithm, really efficient. It's basically an optimization problem. We convert it into a combinatorial process. And so this fairly straightforward, very powerful. Many company and research group using this algorithm as an initial exploratory data analysis for their large data group. And then you using the result of the clustering to do further training of neural network. Okay, and here's the problem. Okay, it is hard to determine how many clusters we have in our data point. So for example, this set of data point I can separate into 2 clusters. It looks pretty good. And we can separate them into 3 data clusters. And we can reassign them to 4, 5, 6, 7, 8, and 9. So they all looks pretty similar, and each one, when you increase the k value, actually you can visualize them. They looks better and better. So which k value is the optimal value in this case? So let's do that. So there's no easy answer to pick a best k value. One way, as we use it in the nearest neighborhood, and other method, we're using the album method, straightforward. And also, the Sequoia coefficient plot is also frequently used for non-hierarchical cluster data. We talk about that in next few lecture. But first of all, calculate the sum of the square error usually, and called the SSE for sum of the k value. For example, 2, 4, 6, 8, and so on and so forth. Then using the SSE to define the sum of square distance between each member to the cluster and its centroid. So let's take a look how this goes. If you plot the k against the sum of square error, you will see that the error decreases as the k increases. So this is because the number of a cluster increase, they should be smaller cluster, so the distortion also be smaller. The idea of the elbow method is choosing the k at which SSE decreases abruptly. So this process is so-called elbow effect in our graph. You can see in the next slide. In this slide, well, we can see that when number of cluster k value increases, actually the inter cluster distance, we call the sum of square error basically, is decreased. Okay, then it start plateau out. So we choose one of the cluster value, this 3 or 4 in this case, may be the best cluster number for us. All right, next we will start out showing you how this to using a scikit-learn's own built-in data generation tool to create some rendering cluster, and then we test these data set with a K-means algorithm. We see so we will talk about that in the next lecture. Hope to see you in the next lecture.